Every system with a finite capacity eventually fails when the load placed upon it exceeds what it can bear. A worker accumulates sleep debt and makes a critical error. A household takes on too much debt and defaults. A nursing home understaffs its floors and receives safety citations. Each of these disciplines measures this extraction pressure using completely disconnected metrics. Sleep scientists use hours of debt. Economists use debt-to-income ratios. Regulators use staffing ratios. Because they don't share a mathematical language, a safety threshold discovered in sleep science cannot be tested against wage extraction. Without a unified framework to measure it, the systemic cost of carrying this load remains invisible to both macroeconomic and epidemiological analysis. To solve this, researchers proposed the Extraction Attenuation Framework, or EAF, a unified, dimensionless measurement architecture. At its core is a single equation: gamma equals load divided by capacity. This index scales from 0 to 1, where 1.0 means load exactly equals capacity. Past this critical threshold, catastrophic failures won't happen gradually. They follow a steep, S-shaped logistic curve. We are going to test this single theoretical equation across 3 structurally independent datasets to see if it holds up to empirical scrutiny. If this equation works, it provides researchers with a universal architecture for predicting extraction failures across seemingly unrelated domains. Our first testing ground is economic wage extraction. Standard labor statistics report nominal hourly pay, but they omit the hidden costs that reduce effective compensation. To calculate gamma for wages, the numerator represents the combined hourly cost burden imposed on the worker: commuting expenses, hours lost to scheduling instability, and gaps in benefit coverage. The denominator is simply the nominal hourly wage. Researchers calculated this index across 11 major economic supersectors, comparing the results against 2022 Bureau of Labor Statistics voluntary quit rates. This scatter plot compares 11 sectors, mapping gamma against JOLTS quit percentages. The data shows a strong, statistically significant rank correlation between wage debt and worker turnover. When restricted to 8 low-wage hourly sectors, the correlation strengthened significantly, a finding that replicated in 2023 data. The metric operates as a forensic screening tool. Sectors where hidden costs extract more of a worker's nominal capacity reliably predict mass worker exit. The second testing ground applies the index to biological sleep debt. The numerator becomes 8 minus the actual hours slept, and the denominator is the CDC capacity baseline of 8 hours. This was tested by cross-referencing sleep data from 16 sectors in the National Health Interview Survey with Bureau of Labor Statistics workplace injury rates. This scatter plot maps sleep debt against injury rates. The dispersed data shows a directionally consistent but statistically weak trend at this core sector level. However, applying a piecewise regression reveals a nonlinear breakpoint emerging right when gamma hits 0.68. This 0.68 breakpoint aligns closely with existing chronobiology literature. It mirrors the cognitive impairment threshold equivalent to a 0.05% blood alcohol concentration. While sector-level data is too coarse for definitive proof, the index's biological formulation successfully detects the shadow of a physiological threshold. The final primary domain tests institutional extraction. Here, we analyze nursing home staffing using a normative capacity benchmark of 5 nurse hours per resident day. The scale of this test dataset is massive. Over 14,000 facilities were analyzed against federal health deficiency citations. This visualization plots all 14,000 facilities. Despite the massive sample size, the expected steep logistic threshold curve completely failed to materialize, replaced instead by a weak, nearly flat linear slope. Formal testing decisively favored the weak linear model over the logistic curve. This happened for 2 structural reasons. A 95% baseline deficiency rate created a massive ceiling effect, and aggregating all nurse types into a single metric masked the daily instability of the actual shifts. Even with massive facility-level data, relying on fixed normative anchors and aggregated variables will obliterate any trace of underlying threshold dynamics. To prove exactly why the nursing home data failed to show a curve, researchers conducted a deliberate methodological null test using household debt. They mapped 20 years of aggregate national debt-to-income time series against mortgage delinquency rates. This chart highlights the expected mortgage default threshold zone, located between 0.20 and 0.35. By averaging millions of households together, the data's range is compressed to a microscopic sliver between 0.10 and 0.13, entirely missing the danger zone. A logistic threshold transition is mathematically impossible to detect if the dataset never approaches the inflection point. Individual households absolutely exhibit threshold defaults, but averaging them into a national index flattens those individual cliffs into a gentle slope, a mechanism known as masking by aggregation. Low-resolution aggregate macro data systematically masks micro-level catastrophic thresholds, smoothing over dangerous cliffs until they look like harmless plains, even when failures definitely exist. These mixed results forced a recalibration. The framework is not a rigid universal law, but a portable screening heuristic. This data requirements matrix outlines boundary conditions for the index to function correctly. Researchers must use high-resolution microdata, and the sample variance must span the suspected threshold. The outcome measured must be a direct adverse event, like a regulatory failure, rather than a distal proxy. Without strictly adhering to these three conditions, extraction pressure will remain statistically invisible to researchers, regardless of how much math they apply. To accelerate cross-domain analysis, the framework provides a Rosetta Stone table in its supplement. This table maps 22 additional, highly testable domains, providing exact definitions and data sources for everything from hospital emergency room loads to airline pilot duty hours to tech API rate limits. Independent researchers can use these open protocols to replicate and test these specific domains. The ultimate value of the framework lies in operationalizing structural extraction into a single dimensionless ratio. With a unified language, researchers can compare biological depletion and macroeconomic decay side by side, giving us tools to manage the extraction pressures dictating our lives.